Okay, let's continue with developmental disorders. There's a couple different reference frames that we like to talk about these disorders from. One is from phonetics, and that's all kind of physical, right? So we're looking at the physical makeup of things. We're also looking at how speech sounds are perceived. So when we're talking about the phonetic science background, there's two different things we can look at with production. The first is the brain, which is generating the motor program. We talked about this a lot in previous lectures, but essentially, Broca's area and the motor strip. This is all in the frontal lobe. These are important for communicating to the effectors what you're actually trying to say. Like, how are you going to say "buh" instead of "puh"? Or how are you going to say "buh" instead of "la"? Or anything like that. There's a motor program that comes from the brain and then goes to the effectors. This is where the phonological problems come in, because something isn't going right in the brain. Then we've got bones and muscles, and we've got the correct program from the brain. The correct motor program is coming down to the bones, to the muscles, which is going to move the bones in a certain way. And if there's a problem there, anywhere, the muscles of respiration, phonation, articulation, any of those, there's a problem anywhere in there, then you're going to have a disorder there too, an articulation disorder. Because the motor program is correct, but the actual production is impaired. So, problem with brain is a phonological disorder, and a problem with the musculature or the shape of the bones or the shape of the tissue, anything like that, that's going to be an articulation disorder. We can also look at perception too. This is usually how we end up learning things. Remember when we talked about fronting versus backing, the reason why things are fronted often is because you can actually see those. You can see a f and a t, but you can't really see a k and a h. Those are back too far to be able to really figure out what's going on there. If you can't hear the difference, or if you're just learning the language and you don't really know how to map on a h to where you're going to make it in your mouth, then it's easy to see these others and you can kind of figure that out. You can use the visual information and the auditory information together. Okay, so here's what I want you to do. If your last name is A through K, I want you to watch the video that I'm going to show you, but mute your sound. Just mute it. Just watch what's happening. And what I want you to do is... Okay, no, I can't tell you that. Just mute it. Just mute right now. Don't listen to anything else. Mute it now, and there's going to be a different video that comes on the screen. Watch the video, and then I'm going to ask you something at the end. So go ahead and mute it now. I'm going to talk to the other people. You don't need to listen to this. Okay. People L through Z. First of all, what about A through K, right? What a bunch of nerds. If you're L through Z, what I want you to do is close your eyes. Just listen to what comes next. That's all I want you to do. You're going to hear somebody else speaking. Okay? All right. This is not the correct video. Sorry. All right. A through K, you shouldn't be hearing me now. If you are, mute your sound. L through Z, you should be hearing me now. And if you're seeing me, then close your eyes. Okay, ready?
ba ba, 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 ba.
Okay, people who are listening to me, you can open your eyes now, and people who are just seeing me, you can turn your sound on now. There's going to be people who just sit there the whole rest of the video with their sound off, and hopefully it's not you. I mean, I guess if you're hearing me say this, it's not you, so that's good. Anyway, I want you to watch this with both senses now. Watch it and listen to it. And I feel like you're going to be blown away by what ends up happening here. It's different than what you thought, I bet.
Ba ba, 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 ba ba.
Okay.
Ba ba, ba ba, ba ba.
So, what's going on is, it's ba the whole time, right? And if you had your eyes closed, you knew that. Well, I mean, I guess I shouldn't say it was ba the whole time. I left my microphone on. Sorry if it was echoey. Anyway, I shouldn't say that it was ba the whole time, because really it was sort of ba the whole time. The audio was ba the whole time, is what I should say. And the visual was ba, then I think da, and then fa. So, ba, da, fa, and that is the visual. The audio is ba the whole time. And so then when you watch and listen to it, you don't actually perceive it correctly in any condition, well, except for when it's ba in both. But it ends up kind of looking like ta-ta or something like that, and then maybe va-va in the end. So this is the McGurk effect, and essentially what's going on here is to figure out speech sounds, we use both senses, both vision and audition, and they're weighted approximately equally. Let me give you, I know you've probably seen this GIF a million times, but I'm going to give you the full experience of this guy's face. So this comes from a video called Italian Spider-Man, by the way, and if you haven't seen it, it's ridiculous. It's kind of funny, and then also maybe it goes on too long, but you should watch it anyway. Not the McGurk effect, but this GIF. Anyway, the McGurk effect is just something from psychology, from perceptual psychology that we know. They seem to be weighted approximately equally, because it's not that most people hear ba, even though they're seeing something different. It's not that most people hear da, even that's what they're seeing, but they're hearing something different. It's more like the two are averaged together. You experience something that's between the two. So ba is spoken, ga is seen, and da is perceived. It's interesting. Oh, so ga is what you saw in the second one. Duh. Okay, sorry about that. It's hard for me to, if I'm listening to it the whole time, it's hard for me to separate it up. Anyway, What's really cool is this works for guitar chords too. If you know exactly what what fingering a guitar chord should be. So if I'm gonna do this, if you play guitar, you probably know what chord this is. But now, like, I can't put the. So that's a G, right? So if you see a G, but I'm playing an A, you'll experience some sort of like, A flat kind of thing, right? If you are really good at knowing what chord is what just by seeing it, and you get audio input that doesn't match that chord, you'll kind of average the two. Also, with tennis balls and beach balls, if you see a gigantic beach ball hit the ground and the sound is a tennis ball hitting the ground, and you ask people, well, how big do you think the ball was? They'll answer like maybe a watermelon size, because we know what a tennis ball sounds like. We know what a beach ball sounds like. And so you're kind of averaging the size information with the audio information, and you come out with maybe a basketball size kind of thing. Really strange. What's really also strange is that we see less of an effect in people with dyslexia. I don't really see the link there. That's really interesting. Specific language impairment and also autism spectrum disorder. It's possible that this split between the two senses, between audition and vision, could maybe be what gives rise to specific language impairment. We know that it's really important for both senses to play a part in speech development. So maybe that's where specific language impairment comes from. Maybe. But it doesn't seem like there are usually, well, sometimes there's other deficits, but there don't have to be other deficits. We'll talk about that later. It's possible. Another one is autism spectrum disorder, and this kind of makes sense to me as well. It's possible that, with the McGurk effect, at least, there is a human component as well. We know that a lot of times eye contact isn't necessarily made, or even contact with another person's face. So they're maybe weighting the audition a little bit more. So it doesn't work as much on them, possibly. The dyslexia is still pretty intriguing. And I'm not sure that that's what's going on with ASD, but I would assume that that's what's going on with ASD. Anyway, that's the McGurk effect. Here's another gift for you. Okay. So let me get rid of my face. Or at least put it up a little bit more. Okay, so we're to right here. Typically, production disorders are articulation disorders. So if you have a problem, producing a sound, that's usually an articulation disorder. So production. Usually it's a bone and muscular problem. It's not usually the brain. That's a little bit more. The phonological disorders are a little bit more rare. Though, of course they happen. They both happen. Articulation disorders are a little bit more prevalent, I guess, is my take-home message from that. The other reference frame that we can use is linguistics. Wait, sorry. Let's not get into that yet. I want to talk about this categorical perception here really quickly. So you can have this. It doesn't really matter what's going on here. Well, it does sort of. It doesn't matter what's going on down here. So what you see on this graph is the percentage of people identifying this sound right here as a B, and it's 100%. The next one over, it looks like maybe it's slightly lower. Maybe it's like 98% of people identify this as a B. The next one, maybe it's 95% of people identify it as a B. And then This one right here is like maybe 30% of the people identify it as a B. And why is that? Well, it's because that sound right here, you can see that these two triangles are right on top of each other. That sound sounds to about 70% of people like it's a D. You change it a little bit more, and 100% of people think it's a D. So what's going on here? Well, this is showing that we don't always produce B's or D's or G's or any sound exactly the same way every time. It's almost impossible. It is impossible for us to produce something exactly the same way every time. We can't. Every B is slightly different. The way the lips come together is slightly different. The voice onset time is slightly different. The way the lips open is slightly different. It's all very slightly different every time. You know, like a snowflake, kind of, I guess. Sort of. Anyway, it's stupid. I've never really looked very closely to snowflake. I think this is because, you know, I live in Arizona, and we don't see a lot of snowflakes. I don't actually have a good concept of what, like, I can make paper stuff. Anyway. But they're supposed to be unique. And it's kind of like every time you say any speech sound, it's a little bit unique. So how do we deal with this? Well, we kind of assume, our perceptual system assumes that there's a little bit of difference in these speech sounds, but these are going to be pretty much the same thing. So we learn that a B and a B are buzz, right? They're both B sounds. But then you get too far away and it becomes something else. So we're okay at lumping things together that should be lumped together. We're okay at saying that these things that are not alike should not be alike. Though sometimes, you know, you have something that a lot of people think is a D that some people think is a B. And maybe it actually is a B. This is where a lot of our speech errors come from. If you're hanging out with a bunch of friends, somebody accidentally says something wrong, they have a momentary accent for 2 seconds because they've said some vowel incorrectly. The motor program went through maybe correctly, and then somehow it just didn't come out right, and it sounded like they had an Australian accent for 2 seconds. And this just happens. We can still understand it, but we perceive it as a different sound. So what's going on with the McGurk effect is that you have some information as B, some information is G, and instead of giving your brain two types of information, one says, I think it's a B, and one says, I think it's a G, you don't get dual perception of B and G, you end up with D. So it's kind of putting the information together. This is all auditory information that we're looking at here, but you can imagine a very similar thing for visual information. When you integrate the two, when you average where the two little triangles would be, then it's firmly within D, and the perception is D. You'll probably see this a lot more when we talk about categorical perception. We're not going to talk about it a whole lot more in this class, but if you take 375 or 367 with me, we'll talk about categorical perception a bit more. It's a cool thing. Okay, so back to linguistics. We can also come at this from a linguistic standpoint, which is looking at knowledge. Knowledge of speech, knowledge of words, knowledge of speech sounds, rules of language. It's a little bit overlaps with the brain part of production. So in the phonetic science area, we might think that there is a neural problem. Neurons are miswired, or possibly there was a stroke, or possibly some neural connection was never made. A linguistic standpoint might look at the rules of language, not really care about what the physical aspect is. It's kind of like, it doesn't really matter what is miswired. It doesn't really matter what didn't make a connection or something like that. What matters is what's the actual rule that was lost. So we can look at it that way. So they're different reference frames. They're kind of looking at the same thing. They're going towards the same area. All right. Cannot advance. There we go. Okay. I'm not going to spend a whole lot of time on this slide. It's not super necessary for your career exactly. But there's something called distinctive features. It's a little old. Distinctive features was that we thought originally that you could break sounds up into distinctive features, right? So what we've got here is like, is the sound back? And then it's either yes or no. Is the sound high? It's either yes or no. And so if you have something like an E, you can see here that the E is, well, it's not on here because these are all consonants. Oh, here's vowels. Okay, so is it back? And for an E, it's got a negative because an E is a very front sound. But an an ah, it's funny that is not back. That doesn't make a lot of sense. But an ah is back, so it gets a plus. So the ah is back, the E is forward. Labial, here it says, if it's labial, it gets a plus. If it's not, it gets a minus. That's just a sound that's using lips. So p, b, f, those are all using the lips, so they get pluses. The idea is that you can break this down into a number of factors, and by the time you have enough factors, you can differentiate speech sounds by the different patterns that they make with these pluses and minuses, or ones and zeros, like that. Well, I think the reason why they came up with this is in the 60s and 70s they came up with this. Chomsky was a big, Noam Chomsky was a huge proponent of this. If you don't know him yet, you will, although I think a lot of you are in my 367 class, so you already know a little bit about Chomsky. I think you know that I don't agree with some of his things. I actually think that the distinctive features hypothesis was like totally cool. Like, it's old and it doesn't hold up, but it's still totally cool. So what the hell was I talking about? Well, oh yeah, binary. So it's kind of like binary, right? So if it's a 1, it's true. If it's a 0, it's false. And the reason why they came up with that was binary was like the highest technology of the day. All of our computers and things in the 60s and 70s are built on binary code. Ones and zeros circuits are on or off. It seems like what happens is we always look at the highest technology that we have and we say, oh, dude, the brain is like that. And so let's make a model based on that because that's what the brain is like. Which is sort of true, but then we have this problem with coarticulation. I mean, first of all, we talked about how a B is never exactly the same. And we've also got problems with coarticulation. I think I have a picture of that. Yes, good, I do. So we have coarticulation is where here's our da is usually in this point in the mouth. So pretty da right here, right on the alveolar ridge. You can feel it. Go say it. Da. Nobody's around. Da. Good job. So, but if you say arda, go ahead and say arda. Your tongue moves back. It doesn't go arda. It sounds a little weird. So you can say da, right where you do, but then arda is back. And you can say ga, or you can say alga, and see how it's moved back as well. So that's coarticulation. We don't say da the same way every time. Even when you're just saying da, there's a little bit of shifting around. But when you say r in front of the da, it moves it back reliably. I mean, our da is not going to come out the same every time, but we do know that r is going to push the da back. So what that means is it's not binary. It's not just one sound can be represented by ones and zeros. It's a little bit more complicated than that. There's like weightings and other things that come off of it. But here's the thing. Now, the height of technology is neural nets, and things are weighted, and they've got probabilistic values and things like that to them, and that's exactly what we think is going on with phonological processes now. So we're doing the exact same thing that they did. In 20 or 30 years, when there's quantum computing or something like that, we're going to say like, oh man, the brain is exactly like a quantum computer, and the phonological processes do this quantum stuff. So we're always getting closer, but we're never quite there. I mean, someday maybe we will be, but I I mean, people talk about distinctive features and how it's not true, but it's really cool. I mean, it's what laid the groundwork for all of our, like Siri, all of our speech recognition and fake speech and stuff like that. It's what helps people who don't have a voice be able to use those artificial voices to produce their own speech. It's really cool. It's great stuff. Okay, that's the end of this lecture. And then let's move on to the next part when you're ready.